All right, guys, so here we go. Our next section I'm going to do is going to be our earthquakes, and this should be pretty interesting. Your goal is, the first part's a little bit of review of what we've already covered, and then I'm going to get into the types of earthquake waves. So get ready, sit back, and enjoy the show. I'm also going to post this exact slideshow onto the Google Doc. So once you're done watching this, you'll also have access to this as well. If you want to use any parts of it for your portfolio, you can add to it. All right. So here we go. First thing we have is stress, as you see on the thing, a force that acts on a rock to change it. Okay. So stress is a force that acts on a rock to change it. We talked about tension, we talked about compression and shearing. All right. Tension, when we take an object and we pull it apart, we cause it to become thinner. So rock gets thinner. Compression squeezes or squishes together, and it also makes it thicker. We did that the other day. So you see it makes it thicker when you push it together. And this is, if you have your graphic organizer handy, this is perfect. This will go right with that as well. So shearing, we talked about shearing. That was a side-to-side motion. Okay, shearing was side to side. And then if you did the fault activity, faults occur along the plate boundaries, and it's when stress builds up and the rock breaks and it causes a fault. Not my fault, it's your fault. Now, we talked about crusts also earlier this year. We have the continental crust and oceanic crust. Remember, the continental crust is thicker. We're going to be learning about rock soon, and it's made of granite, which is a lower density rock. The oceanic crust is made of basalt, so we have that as well. So basalt is very dense. So when you have an oceanic crust coming in contact with a continental crust, a lot of times you'll get the oceanic crust diving under or subducting. Quack, yep, I heard it. Subducting under the continental crust. When you have two continental crusts coming together, a lot of times they'll collide and they'll actually cause mountains to form. All right, so let's move on to this other stuff here. Let's see. So if this were a class, this is how we started off. I have a little intro slide, and what you can see, I want you to look at some of these pictures. These railroad tracks, see how they're shifted? That's from shearing, okay? That would be a side-to-side, a shearing thing. And over here, you have plowed fields, and you see how that shifted as well. Yes, I have a bear upside down in a crevasse. All right. If you did the faults exercise, I'm going to go through this very quickly again because I did it as a separate activity. We hand drew it the other day. Or if you did not see the faults activity, this is what you'll do, and I'll take my time and draw it with you. But we have inside an earthquake. We have the fault line, which was the point inside the earth where the rock is broken. We also have the focus, which is the point inside the earth down here where the rock starts to break. We have the epicenter, which is the point directly above the surface where the energy actually hits first. And now on to what I really want to talk about in today's lesson. Again, the parts of a fault was an activity we just did. I did it in another, trying to find my page here. We did it with another activity. I recorded it, and it's a pretty good diagram we drew. Seismic waves, here we go. There are three, count them, 1, 2, 3, three types of seismic waves. So what we're going to do today is we're going to talk about the different types of waves. Now, this is what they teach all the way up through high school. There are three types of waves. Please try to, some kids think this is funny for some reason. I don't know why, but we'll see. First wave, number one. Number one is the P wave. P is number one. P stands for primary, okay? So you can think about it, PP, primary, number one. So each wave has a letter for a name. It also has a word for a name. P, number one, primary. Now, a primary wave has a push-pull. So it's a push-pull motion. P can travel, the P wave, sorry, it can travel through solids, liquids, and gases. It's first to arrive. It's very fast. Don't ever underestimate the power of the P wave. Okay, nothing can stop it. It comes without warning, and it's just there. Boom. So P is number one, P wave, push-pull, primary, solids, liquids, and gases. P can go through everything, the P wave, and it's first to arrive, and it's really fast. So look at all this P here, P, 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 okay, and I highlighted it for you. So P, primary, push-pull, all P's. All right. Whew. So if number one is the P wave, number two has to be, give you a second, think about it. Number one is P, number two has to be S. There's only one thing S could stand for when it's talking about seismic waves, and that is a secondary wave. I hope that's what you were thinking. So secondary, number two, S wave. The motion of an S wave is side to side. Yep, and solids only. So the S wave, number two, can only travel through solids. Yeah. It's also slower. It's second to arrive. It takes longer than the P wave. You know, the P wave gets there first, and sometimes you're just hanging out, chilling out, sitting there, you know, reading the magazine or whatever, and then all of a sudden the S wave arrives. So, and that's going to be very important later. We'll talk about that later. But the S wave is a side-to-side motion, where the P wave was push-pull. S wave is side-to-side. It's also slower, and it's second to arrive. So there you go. There's your information. And look at this. This is full of S. There's S everywhere. There's S, 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 S. So how do you remember secondary wave? Because of the S. S, secondary, side to side is the motion. Starts with S. Solids only, slower, second to arrive. Okay. This is one of my favorite lessons to do in the classroom. I wish I was in there with you guys right now. All right, the third wave, number three, the final wave, the one that causes the most destruction, when the S wave actually reaches the surface and some of it transfers into this final wave. It is the one, the only land or surface wave. Now, the motion of a land wave is up, down, and around. So if this is the surface, it's just my phone case here. If this is the surface, it would go up, down, and back around. So we have the P wave, the S wave, and the L wave. So if you picture this side of the house rising up 6 feet and this side of my house dropping 6 feet at the same time, buildings don't like to do that. So the L waves are some of the most destructive waves. They're the ones that cause the most damage. Remember, earthquakes don't hurt people. It's our buildings and the things we build that can't hold up to an earthquake falling on people. So earthquakes are obviously much more devastating if you're in the cities or in areas where there's very prone to like steep hills or landslides. But mostly it's our stuff we build that hurts people in an earthquake. Keep that in mind. But the L wave, back to that L wave, slowest, it takes the longest to arrive. The P arrives, then the S, and then you're going to wait a while longer, and then the L hits. The L wave is like an ocean wave going across the actual ground. It's devastating. And it can travel through solids and liquids. It's the slowest to arrive. And the motion is up, down, and around. All right. So before moving on, real quick review. Number one. What was it? Number one. P. P stood for what word? Primary. The motion, remember, PP. Push, pull. First to arrive, and it travels through solids, liquids, and gases. Okay, remember number two, wave number two. S wave stood for what word? Secondary. Side to side was the motion. It was slower than the P wave. Second to arrive. And it only traveled through solids. Now remember, we knew that the outer core around the Earth was liquid, and the inner core was solid. We found out about that outer core being liquid because those S waves, as they traveled through the Earth, hit the outer core and they stopped. And the P waves kept going. So because the S waves do not travel through the liquids, they stop. All right, so why is it important about this P and S wave situation because the difference between the arrival times. You say the P wave always travels as fast as the P wave will travel. The S waves have a known speed that's slower. So when we take the difference and when these waves arrive at a certain point, we can tell something really powerful. That's how far away that earthquake was. So that's what these next couple slides are about. So the P wave arrives, and the seismograph is a seismometer is the machine that records earthquakes. A seismograph sheet here is what this would look like. So the P wave makes a mark, and then let's say there's a 2-minute wait before the S arrives. And then seismic station B, the P wave arrives, and then there's a minute break between the P and the S waves. The C, P arrives, and there's 0 seconds, and the S arrives right away. Using this information, and in high school, you'll actually use a graph and all these the charts to figure out exactly how far it is. We can find out how far an earthquake is. So let's take A. Once we put the math into that P and S arrival time, it tells us a distance. Now let's say this was 120 miles. So one of you, I send out hiking on this 120-mile radius, to find that epicenter. That's not going to work. So what we can do is we take that seismic station B, and we take the distance between the P and S waves. Now the epicenter must be on both points. So if one of you are walking this line, and the other one's walking this line, the epicenter must be on both points. So this point here, you'd be like, hey, how you doing? No, how you doing? And over here, the person A would be, hey, how you doing? Person B would be like, no, how you doing? It's got to be one of those two spots. How do we find out exactly where it is? We need seismograph C. So we take the third one, and now, can you see where it is? Can you see where all 3 circles come together? Right here. So right here, we'd have C and B like, hey, how you doing? No, how you doing? And A and C, hey, how you doing? How you doing? And up here, there's only one spot on this chart. It's right here, where all 3 people are going to be going, hey, how you doing? How you doing? No, how you doing? And that right there is going to be your epicenter. That is the triangulation. That's the point where all 3 come together. Now, in real life, we have thousands and thousands of seismographs giving these circles. And when they all come together, at that one point. That's your epicenter. Remember, your epicenter was the point directly above the focus on the surface where the energy first hits. All right. So here you can see we've triangulated that spot right there is the epicenter. All right. Now the Richter scale. Now let me just explain this a little bit. If I tell you the earthquake was a 1.0 on the Richter scale, and the next earthquake was a 2.0 on the Richter scale, is a 2.0 twice as powerful as a 1? Think about that. It's not. Matter of fact, it's about 32 times stronger. So a 2.0 on the Richter scale is the same as 32 ones. Let's take a stick of dynamite, for example. A 1 Richter scale is 1 stick of dynamite. This is not a stick of dynamite, but let's say it was one of these. To get a 2.0, I would have to stack 32 together. So that box shows 32, big stack of 1s to get a 2. How about to a 3? Let's look at a 3. Is that 2 2.0s? No. It's 32 2.0s. So it's a magnitude higher. It's a much more powerful earthquake. And this, you don't even feel an earthquake up to a 4 or so. But when we're getting to an earthquake like the size of a 6 or a 7, the difference between a 6.0 and a 7.0 is not just a little bit. A 7.0 is like 32 times stronger than a 6.0. And now go to an 8.0. That's 32 times stronger than a 7. Now think of these 9.2s that caused a huge tsunami in Japan in 2011. That changed the rotational speed of the Earth in a measurable way. It was so powerful and caused a tsunami that killed 30,000 people. That was a 9.2. Or back in 2004, the Boxing Day tsunami in Indonesia, another 9.0 earthquake. It was insane. It killed 300,000 people with a resulting tsunami. So when we say an 8 or a 9, that's huge difference. So understand that the one number doesn't mean just a little stronger. It's a whole magnitude stronger. All right, very cool. All right, guys, quick review here at the end. We're going back to these plate boundaries. When we had a plate boundary that was pushing together, do you remember what it was called? We can't click and reveal because this is a PDF. Coming together, the plate boundary. Now, some of you might have said compression, which is the stress of pushing together, but what plate boundary was it? If you said convergent, you were right. How about pulling apart? Now that you know convergent was one of those plate boundaries. Pulling apart. If you have your graphic organizer, it's a great thing to look at really fast. Pause the video if you want to go back to it. Pulling apart was divergent. And remember, the way I remembered that, 2 roads diverged in the wood. And I took the one less traveled by. And that has made all the difference. So divergent means pulling apart. And that poem, by the way, is from Robert Frost. I encourage you to go read the whole thing at some point. My favorite, on a convergent plate boundary, you see it, subduction, quack. It's when one plate dives under the other. Remember that. Subduction, quack. One plate dives under the other. If you weren't there when I did the subduction activity, the word subduction, the way to remember the word and what it is, a submarine, a duck in the ocean. Sub, the Aflac duck in the sub, Aflac, diving, quack, 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 quack. Subduction. So every time you see it, hear it, or read it, you may quack out loud. All right, guys. Divergent plate boundary makes a mid-ocean ridge or a rift valley, okay? Mid-ocean ridge or a rift valley. It pulls it apart. And remember the scientist's name that discovered the mid-ocean ridge during World War II while he was on that sonar ship. Give you a second. Think about it. What was his name? Harry Hess. And his discovery of the mid-ocean ridge and seafloor spreading made this other scientist, see if you remember his name, 60 years prior, become not crazy. Who was that? Alfred Wegener, you got it. And then the bonus question, obviously, the Canadian scientist that worked a little bit alongside with Hess and a little bit after, saw that all the earth was broken into these plates, these eggshells. And he put together Alfred Wegener's material and Harry Hess's material and came up with the science of plate tectonics, which is what we use today. And his name, John Tuzo Wilson. All right, great job. Hopefully you got that. If you didn't, you can go back and study it. That's fine. And that is the last slide I have for you guys today. So again, I will be redoing this lesson if we come back back in the classroom. However, if not, then I hope you enjoyed it. Yes, this was a Zoom meeting with just me. I wanted to make sure I could get it recorded for you guys so you could do it on your own when you needed to, and we had a record. However, I will ask you about this lesson on our next Zoom meeting. Anything, what you thought about it, if anybody did it and maybe didn't laugh. I don't know why everybody laughs. I don't want to know. But guys, be safe. Have a great, great day, and we'll see you soon. Take care.